So continuing with the free damped motion, we looked at various situations. We looked at the overdamped system where we had lambda squared minus omega squared strictly greater than 0. And now we'll consider the situation where lambda squared minus omega squared is 0. And this system is called critically damped. Okay? Here we obtain one repeated root and we get this general solution. Let's look at an example. So a mass weighing 8 pounds stretches a spring 2 feet, assuming that a damping force numerically equal to 2 times the instantaneous velocity. So that's giving us our beta. Acts on the system, determine the equation of motion if the mass, and here is now initially released from equilibrium. So x of 0 is 0 because equilibrium is the 0 point. With an upward velocity of 3 feet per second, this minus sign despite the upward because we consider the positive to be pointing down. And we just translate the word problem. So we get k because we know that when we apply 8 pounds, we get 2 feet extension. Okay. So we get our k, we get the mass from looking at the weight over gravity, because weight is equal to mass times gravity. And we have our beta there from this 2 times the instantaneous velocity. And here's our initial conditions. And then we just plug them into the differential equation. Looking at this differential equation, we get, we see that lambda squared minus omega squared is equal to 0. And so the system is critically damped. And here goes our general solution. We fix the constants by the initial conditions. Okay, we just apply the initial conditions. And we obtain C1 and C2 there. And we get our solution. Okay. In critically damped systems look similar graphically. If you consider this the T and X, they look similar graphically to what goes on in the overdamped system.